On the northern edge of Los Angeles, fresh water spills down two stark concrete chutes perched on the foothills of the San Gabriel Mountains, a place simply called the Cascades. It's a deceptively simple-looking finish line, the end of a roughly 300-mile or 500-kilometer journey from the eastern slopes of the Sierra Nevada into the city. On November 5th, 1913, tens of thousands of people climbed these hills to watch the first water arrive. When the gates finally opened, water trickled through, but that trickle quickly became a torrent. The project's chief engineer, William Mulholland, leaned over to the mayor and shouted the line that's been repeated ever since. "There it is, Mr. Mayor. Take it." That moment was profound for a lot of reasons, depending on where you live and how you feel about water rights. LA didn't become LA by living within the limits of its local resources. Its meteoric growth into the metropolis we know was enabled by an early and extraordinary decision to reach far beyond its own watershed and pull a whole new river into town. Today, roughly a third of LA's water comes from the eastern Sierra through the Los Angeles Aqueduct system. That share swings with snowpack, drought, and environmental constraints, but this one piece of infrastructure helped turn a water-limited town into a world city. It's one of the most impressive and controversial engineering projects in American history. But to really appreciate that water in the Cascades, you have to look way upstream and see what it took to get it there. It's gravity, geology, politics, and human ambition all in a part of the state that most people never see. Let's take a little tour so you can see what I mean. I'm Grady, and this is Practical Engineering. When most people think about aqueducts, this is what they picture. A bridge carrying water over a valley or river. And just to be clear, these are aqueducts, but engineers often use the term more broadly to describe any type of conveyance system that carries water over a long distance, from a source to a distribution point. Could be a canal, a pipe, a tunnel, or even just a ditch. In the case of the LA Aqueduct, it's all of them, plus a lot of supporting infrastructure as well. From the center of the city, it's about a 4-hour drive to the Owens River diversion weir. It's not accessible to the public, but it is the official start of the LA Aqueduct, at least when it was originally built. Here, all the snowmelt and rain from a huge drainage system between the Sierra Nevada and Inyo Mountains funnel down into the Owens River, where a large concrete diversion weir peels nearly all of it out of its natural course and into a canal. This point is roughly 2,500 feet or 750 meters higher in elevation than the bottom of the Cascades at the downstream end, which makes it obvious why LA chose it as a source. The entire aqueduct is a gravity machine. There are no pumps pushing the water toward the city. Half a mile of elevation change feels like a lot until you realize you have to spread it out over 300 miles. It's all achieved through careful grading and managing elevations along the way to keep the flow moving. That care is particularly important in this upper section of the aqueduct where the water flows in an open canal. To do this efficiently, you need a relatively constant slope from start to finish. That's a tough thing to achieve on the surface of a bumpy earth. Following a river valley makes this easier, but you can see the twists and turns necessary to keep the aqueduct on its gentle slope toward LA. If it seems kind of wild that the city would buy up the land and water rights from somewhere so far away, it did to a lot of people who lived in the Owens Valley too. A lot of the acquisitions and politics of the original LA Aqueduct were carried out in bad faith, souring relationships with landowners, ranchers, farmers, and communities in the area. The saga is full of broken promises and shady dealings. Then, when the diversion started, the area dried up, disrupting the ecology of the region, making agriculture more difficult and residents even more resentful. Many resorted to violence, not against people, but against the infrastructure. They vandalized parts of the aqueduct, a conflict that later became known as the California Water Wars. In one case in 1924, ranchers used dynamite to blow up a part of the canal. Later that year, they seized the Alabama Gates. About 20 miles or 35 kilometers downstream from the diversion weir, a set of gates sits on the eastern bank of the Aqueduct Canal. Because it runs beside the river valley, the aqueduct captures some of the water that flows down from the surrounding mountains, in addition to what's diverted out of the Owens River, particularly during strong storms. That means it's actually possible for the canal to overfill. The Alabama Gates serve as a spillway, allowing operators to divert water back down to the river. This also helps drain the canal for maintenance or repairs when needed. Those Owens Valley ranchers understood exactly what the Alabama Gates controlled. Open them and the water would run back where it had always run, down the Owens River instead of south to Los Angeles. The resistance simmered and flared for years, but it didn't end in the dramatic showdown at the aqueduct. Instead, it ended at a bank counter. The Inyo County Bank was run by two brothers who were also key organizers and financiers of the resistance campaign. In August 1927, an audit revealed major shortfalls and ongoing embezzlement, and the bank quickly collapsed. Residents across the valley saw their savings wiped out or frozen overnight, shattering what was left of the community's ability to keep fighting. The Alabama Gates weren't just a political flashpoint, though. They also marked an important dividing line in the aqueduct's design. LA knew that even if the ranchers didn't release the water to the river in protest, a lot of it would end up there anyway through seepage. As the canal climbed away from the valley floor and crossed more porous soil, it would naturally lose its water through the ground. So, at the Alabama Gates, the aqueduct transitions from an unlined canal to a concrete-lined channel. It's still open to the air, so there's no protection against evaporation or contamination, but the losses to the ground are a lot less. This design continues for about 35 miles or 55 kilometers through the valley. Along the way, the aqueduct passes the remains of Owens Lake. Once a large body of water, it quickly dried up with the diversion of the Owens River. Of course, there were impacts to wildlife from the loss of water, but the bigger problem came later: dust. All the fine sediment that settled on the lakebed over thousands of years was now exposed to the hot desert sun. When the wind picked up, it filled the air with fine particulates that are dangerous to breathe. Over the years, there have been times when Owens Lake is the single largest source of dust pollution in the entire country, and LA has spent more than $1 billion just trying to fix this problem alone. The aqueduct passing along the hillside past the lake and its challenges is a reminder that the true cost of water is often a lot more than the infrastructure it takes to deliver it. So far, it might be obvious that this aqueduct system is pretty fragile to be making up a major part of a city's freshwater supply. Even beyond the vandalism and political resistance, there are lots of things that could go wrong along the way, from bank collapses, earthquakes, diversion failures, and more. That's why Highway Reservoir was originally built in the narrow saddle between two hills as a kind of buffer. With a dam on either side, it stored up water so the aqueduct could keep running even during a disruption upstream. It also slowed the water down, exposing it to the hot desert sun as a natural form of UV disinfection. In the 1960s, the reservoir was reconfigured into two basins to add some flexibility. That's because around that time, the LA Aqueduct became two. While the open-top canal section was large enough to meet demands, the underground conduit in the next section wasn't, so LA built a second one in 1970 to increase the flow. If you look at this map of the Highway Reservoirs, you can see that water has two paths. It can flow into the second aqueduct here from the North Basin, or it can pass through the Merritt Cut to the South Reservoir, through the intake there, and into the first aqueduct. This setup allows for some redundancy, along with regulation and balancing of the flows between the two aqueducts. Highway marks the start of the long desert run, with both systems no longer in open-topped line canals, but running underground in concrete conduits. There are a lot of advantages to running an aqueduct in a closed conduit underground, especially one this long through a desert landscape. There's far less evaporation and less potential for contamination. It doesn't divide the landscape at the surface level, so there's no need for bridges, culverts, and wildlife crossings. Going underground also offers more flexibility when it comes to topography. You don't have to follow the contours of the surface so carefully because if you come to a hill, you can just dig a little deeper to keep the constant slope. Of course, those benefits come with a cost. An underground conduit is more expensive than a simple channel on the surface, and not all the problems with topography are solved. This is Jawbone Canyon, one of the biggest drops for the first aqueduct. Rather than taking a major detour around it, the aqueduct descends 850 feet, or 250 meters, and then ascends back up. This type of structure is often called an inverted siphon. I've done a video on how these work for sewer systems, and I've also done a video on flood tunnels that work in a similar way, if you want to learn more after this. Unlike the concrete conduit, which really just acts like an underground canal with a roof, this is one of the places where water in the aqueduct is pressurized. 850 feet of water column is about 370 psi, 26 bar or 2.5 megapascals. It's a lot of pressure. These sections of pipe had to be specifically manufactured on the East Coast, where the major steel facilities were, and transported by ship because of their size. They traveled all the way around Cape Horn since the Panama Canal was still under construction. There are actually quite a few of these siphons crossing canyons in this section of the aqueduct, but Jawbone Canyon is the biggest one. A little further downstream, the LA Aqueduct crosses the California Aqueduct, part of the State Water Project. That system has a connection to LA as well, but this branch at the crossing actually heads to Silverwood Lake. However, there is a transfer facility recently completed that can pump water out of the California Aqueduct directly into the first LA Aqueduct. This creates opportunities for LA to buy water that moves through the state system and offers some flexibility in where that water ends up. There's also a turn-in that can move water from the LA Aqueduct into the California Aqueduct for situations where trades make sense. The second LA Aqueduct passes underneath the State Canal here. And this is a good example of the differences between the first project, built in the 1910s, and the second one, built in the 1960s. Over that time, the price of labor went up a lot more than the price of materials. Where the first one carefully followed the existing topography with bends and turns to minimize the need for expensive pressurized pipe, the second one could take a more direct path, reducing labor in return for the more specialized conduit materials. After wandering more than 100 miles or 160 kilometers apart, the two Los Angeles aqueducts come back together at Fairmont Reservoir in the northern foothills of the Sierra Pelona Mountains. This is the last major topographic barrier on the way to Los Angeles. There was no way to go up and over without pumps, so instead, they went straight through. The largest project was the Elizabeth Tunnel. Here, the two aqueducts come together again into a single watercourse. About 5 miles or 8 kilometers of excavation through everything from hard rock to loose, wet ground became one of the most difficult parts of the entire project. The tunnel required continuous temporary supports along most of its length, followed by a permanent concrete lining. It was a monumental effort for its time and essential not only to cross the range. The Elizabeth Tunnel also delivers that water under pressure to the San Francisco Power Plant No. 1. This is the largest of the 14 hydroelectric plants that run along the aqueduct, capturing some of the energy from the water as it flows downward toward LA. These plants are a major part of how the project paid for itself, and they continue to serve as an important source of electricity in the region today. Continuing downstream, Bouquet Canyon Reservoir adds another layer of operational flexibility. It helps regulate flow through the power plants and provides additional storage, a sort of insurance policy since this whole reach depends on a single major tunnel crossing the San Andreas Fault. In case of a major earthquake, it'd be best if Angelenos could avoid a simultaneous water shortage. The aqueduct splits again just upstream of the San Francisco Plant No. 2, which was famously destroyed by the St. Francis Dam failure. That reservoir project was designed to supplement the storage capacity along the aqueduct, but the dam failed catastrophically in 1928, just 2 years after it was completed, killing more than 400 people and destroying several parts of the aqueduct as well. The tragedy was one of the worst engineering disasters in American history. It put another stain on the aqueduct project, and it effectively ruined the reputation of William Mulholland, who was largely considered a hero in LA for all his work on the aqueduct and the city's water system. The dam was never rebuilt, but the workers restored the aqueduct to functioning service in only 12 days. At Drinkwater Reservoir, the two aqueducts run roughly parallel through the Santa Clarita area, sometimes above ground and sometimes below, before finally reaching the terminal structures that carry water into LA. Usually the water stays in the conduits which feed the two hydropower plants at the foot of the mountains. If the plants are out of service or there's more flow than they can handle, you can see the excess water thundering through the cascade structures instead. From here, the aqueduct drops out of the mountains and into the north end of the San Fernando Valley, where the water is treated and prepared for distribution. After filtration and disinfection, it's stored in the Los Angeles Reservoir, the system's terminal reservoir, so the city can smooth out day-to-day swings in demand even while the aqueduct's inflow stays relatively steady. For most of Los Angeles' history, that finished water storage was out in the open air. But in the 2000s, drinking water rules pushed utilities to add stronger protection for treated water held in uncovered reservoirs. There's a good chance you've seen their solution on the Veritasium channel or elsewhere, 96 million plastic shade balls that act like a floating cover, blocking sunlight to prevent water chemistry problems and helping keep wildlife out. They're the final protection for this water that traveled so long to reach the city. While the LA Reservoir is, in a sense, the end of the journey for this water, the original diversion way back at Owens River isn't even technically the start anymore. In 1940, LA extended the aqueduct system upstream northward by connecting the Mono Basin and funneling its water through tunnels to the Owens River Basin. Like Owens Lake downstream, Mono Lake began drying out as well. And also like Owens Lake, lawsuits, court orders, and environmental regulations have tempered the value of this water source, forcing LA to significantly reduce diversions and implement costly restoration projects. That's kind of the story of the LA Aqueduct in a nutshell. The project seemed obvious from an engineering perspective. There was lots of snowmelt in the mountains. The city had the technical prowess, the funding, the elevation, and the political power to reach out and take it, and the result was one of the most impressive works of infrastructure of the early 20th century. And continued efforts to expand and improve the system have made it even more efficient, flexible, and valuable to the many millions of people who live in one of the most populous cities in America, delivering not only water but also hundreds of megawatts of hydropower. But in many ways, it was not only unscrupulous but also short-sighted. Residents of the Owens Valley watched ranchland and farmland dry up as the water that had shaped their home was rerouted south. Native communities saw their homeland transformed with access to gathering areas disrupted, places made unrecognizable, and cultural ties strained by changes they didn't choose. Wind picked up alkaline dust from dried lake beds, habitats were disrupted, and the birds that depended on these waters and wetlands lost part of what made this migration corridor work. It's easy to see why the aqueduct remains controversial and why what we sometimes dismiss as red tape around major infrastructure is often completely justified due diligence. As engineers and really as humans, we have to try and account for costs that don't show up on a balance sheet, but can come back later as decades of lawsuits, mitigation, and restoration. And even the aqueduct's original thesis that there's reliable snowmelt up there and a growing city down here is starting to falter. In recent decades, the mountains have delivered less predictable runoff, more swings, more years when the timing is wrong, and more uncertainty about what normal even means anymore. California's climate has always moved in long cycles, but the margin for error is thinner now, and no one can say with much confidence when or if the moisture the state depends on will return to its old pattern. The hopeful part is that this is exactly where engineering makes a difference, at the messy intersection of geology, climate, culture, politics, and human need. The Los Angeles Aqueduct is a case study in what we can build when we're ambitious, but also what happens when we treat a landscape like a machine with only one output. The next era of water engineers can learn a lot from it. I mentioned the California Aqueduct as another of the large systems that brings water to LA, but there's actually a third long-distance aqueduct that delivers water to Angelenos, this one coming all the way from Lake Havasu on the Colorado River. Like the Owens River project, that one came with its own set of challenges, controversy, and impressive feats of engineering. My friend Sam from the Wendover Productions channel talks about that, plus all the interplay between politics, growth, drought, and engineering in his incredible documentary, The Colorado Problem. It's basically an hour-and-a-half Wendover Productions video with excellent graphics and interviews, and if you want to watch it, it's only available on Nebula. You probably know about Nebula now, even if you're not subscribed. It's a streaming service built by and for independent creators. No studio executives deciding what gets the green light, and no advertisements either. It's just independent creators making stuff they're excited about with as few barriers and distractions as possible between you and us. My videos go live on Nebula before they come out here, and my practical construction series was specifically produced for Nebula viewers who want to see deeper dives into specific topics. I know there are a lot of streaming platforms out there right now, and no one wants another monthly cost to keep track of, but I also know that if you're watching a show like this to the end, Nebula's library of videos is right up your alley. So I've made it dead simple. Click the link below and you'll get 50% off an annual plan. Or if you have subscription fatigue but still want to support what I'm doing, you can get a lifetime membership. Pay once and have access for as long as you and Nebula last. Hopefully that's a long time. If you're with me that independent creators are the future of great video, I hope you'll consider subscribing. Thank you for watching, and let me know what you think.